um, 2 points of organization after we had already scheduled everything today, we discovered that at 6 o'clock, Nima Kanihamid is giving a popular lecture on what we can expect from the LHC. And there's no one I'd rather hear talk about that subject. So we propose to you to have the second talk, rather than being 5 to 6, we'll take a short break after this talk and have it immediately. So something like 4:45 to 4:45, so that people can go to this talk if you like. This talk is in the dining hall. If you go into the dining hall, you'll see a lot of people. Not where you usually sit, but you'll find it easily. That should presumably be about a half hour, 45-minute talk. Second, we'll then have our traditional dinner after that at the Kaluri Corner. So think about whether you would like to join. We'll go over there and start dinner at around 7. And so think about whether you'd like to join, and I'll get a head count for that then at the end of my talk. And we can confirm our reservation. Okay. Everything I'm going to say is joint work with Ben Feinhardt, who's here. Yes, he is. Great. So he can answer all the questions. I've been interested in studying the topology of complicated spaces. So that's an example of a complicated space. This is a branched polymer. I'll say quite a bit more. The plan of my talk is there'll be more or less four independent things of perhaps not all the same duration, but the whole point is that you put together some very different elements and then you get something interesting at the end. So, right, well, there are a lot of complicated spaces in nature. For example, the distribution of the stars in the universe, or for example, the rings of Saturn, or for example, the structures associated with grains in a little sample of metal, or many structures in biology. And these structures have in common that, as I say, they're extremely complex. One is interested in studying them statistically, and they have in common that traditionally topologists have ignored them. The history of topology, of course, has in Poincaré's second paper, it was about cell complexes, and it sort of expanded over the years to include differentiable manifolds, singular spaces. Now, as you've been hearing, symplectic manifolds. But I actually believe that there's an expansion in the Wing's weighting to include complicated spaces like this. And as always with these expansions, you have to rethink what the questions and methods of topology are. Right, so here we have a very, in my talk today, all of the systems studied are going to be contractible spaces. This is a choice partly to sort of eliminate the idea that maybe you want to take the homology or any of the classical invariants of a space. So what can you say about contractible spaces? And actually, in most cases, the homeomorphism type is also not very interesting. Let me give just an example. This is what's called a branch polymer. As I said, I'll define that later. This is what is called a Brownian tree. Now, I think in the limit, these two things are homeomorphic. But in any case, homeomorphism questions are not much of interest. Metric questions are. Traditionally, topologists thought of a metric as just something that would help you along to get your topology, but that's wrong for these spaces. You actually care about distances. Perhaps you only care about the metric up to a conformal transformation or something like that, but you do care about it. Second, I should say there are qualitative differences. Ben and I have been playing with these pictures for ages, and we've had these slides laying. Not once have we confused one for the other. They look different to the eye. You can see that. Well, topologists ought to be able to measure and say they're different in the following way. But as I say, the traditional invariants of topology aren't up to the task. So what should we do? Well, actually, if you look at this, actually, from where you're sitting, you may not be able to see that it's contractible. You may actually think that there's a loop here. Well, there's not. There's actually a little opening right there that I can see. Anyhow, that's the idea. The idea is, instead of looking at the topology of the space, stand back a little bit and blur it. So the way we'll formulate that is let's let x bar r be the radius r neighborhood of x. All the spaces I named are naturally embedded in Euclidean space, and I'm going to assume they are, but actually the invariants I'm going to define only depend on x as a metric space, abstract metric space. Then we'll look at the groups hi of xr. So I'm going to talk about that, the homology groups of an R neighborhood. An R neighborhood is what you get when I do that. Okay, so instead of having a sort of a, I mean, where's a good one? Here's a nice thing which almost closes, or I had one that actually, here's one that you actually can't even see probably from where you are, whether it closes. Well, typically for a mathematician, I'd like to sort of abstract that. Let's take just as something to study, let's take a circle and take an arc out of that circle, and then start taking various neighborhoods of this. Well, as I start taking neighborhoods, first of all, nothing happens to the topology, and then there's a certain moment here where all of a sudden there's a change. And then as I continue along, again, nothing happens for a while. But at a certain moment here, there's another change, and my R neighborhood looks like that. So what's happened on the R axis, we have a certain moment. The first change was the moment where we had a birth of a homology class. In this red picture, there's a homology class which runs around this, which captures that hole in the space. And there's another point where we have the death of a homology class, of that same homology class in this case, because there's only one. And so to that homology class, we can associate two numbers, a birth time and a death time. Now, the goal is to play with those two numbers, and well, there are various coordinates, and none are necessarily better than the others, but here's one that has a lot of good things going for it. Here we take the log of the birth plus the death, if you like, over 2. And here we take the arc secant of the death divided by the birth, which is a number that goes between 0 and pi over 2. And this, okay, so why the arc secant? Well, that's just well, the easiest thing to see is that there's a number I can associate to this, which is this angle theta here, and that's equal to theta. That is, if I okay, so if I took away more than half of my original circle, then no matter what neighborhood I take, I never get any homology classes. So we don't see anything. So I have to have at least half of the circle left, and so if I take my semicircle and add an arc of length theta on both sides, then I have a shape, and that shape will be this y coordinate. So I like to think of this axis as the size axis, and this is the shape axis. Shape because it involves theta. So if I imagine drawing various circles, here I have things which are just a little bit more than a semicircle, and they come in different sizes. They're all similar to each other, but they get scaled down exponentially. So I'm plotting the point. So from the thing, I associated using homology, a birth and a death, and from that I associate a point here, and I'm plotting that point. Over each point, I'm putting the picture of a semicircle which gives rise to that point. So up very, very close to pi over 2, we have semicircles that very nearly close, and again, they come in various sizes. Okay, so that's in a sort of a complete exploration for what happens with single arcs of circles in dimension 1. So up here I was doing H1. If I do H2, well then I get a similar picture, except that now I have a sphere with a piece cut off. Paul said to make a sphere you do that. So that's a piece of a sphere with a thing cut off. If this is the center of the sphere, then this is angle theta. And again, if I do the same thing with the sphere and I take H2, again I have a similar picture, except that these would be spheres. So it's somehow measuring how much of the sphere has been cut out. Okay, well let's do this with a sample material. So here's a branched polymer, which we in the mathematical idealization, as you'll see, is a whole bunch of circles which are tangent to each other. And now I start taking epsilon neighborhoods of it. The first epsilon neighborhood looks like that. So you can see, even though the original thing was contractible, I already have homology classes which have been born, the second epsilon neighborhood looks like that. This, of course, really should be on a personal computer growing. But now the previous ones have actually all died, and I have a few others which have been born. But this big one is still here. And then I take a further epsilon neighborhood, and by now this big one, which has been sort of the central story of the thing, is the only thing left. And I take a bigger epsilon neighborhood. It's still the only thing left, and actually I don't have a picture of when it dies, but you can see what's see what you have. So in the case of a complicated sample, you have an axis, and you have a whole bunch of I don't mean that these should be equally spaced, and I want the same number of each. 1, 2, 3, 4, 1, 2. Okay, so you'll have something like that. Now, there's only one magic statement here, and this is due to Edelsbrunner and Zamarodian originally, but in an audience like this, at least for okay, so I'm going to give it. So here you would imagine it might be hard to associate which, here's a birth. Which death should I associate to it? I'd like to get a whole bunch of points. I would like to summarize this material by a diagram of the following type, which is going to be the central object that I'm going to be talking about all the time. So a scatter plot of a whole bunch of homology classes, each of them representing a birth and a death of a single homology class. And these are with the coordinates that I've expressed. In order to do that, you have to figure out which death goes with which birth. Well, since this is Marston-Morse week, let me tell it in a different way from the way Edelsbrunner and Zamarodian did. In some sense, Marston-Morse's deepest discovery was that sheaves over the real line are extremely simple. You can completely understand them. So you can, but that's what we have. We have what I was just showing you, this family of spaces. This, for each point on the R line, it gives me a space. So that gives me a space for each point on the real line. That's a continuously varying family of spaces. Leray and Grothendieck already showed how to get a sheaf out of that, so you get this algebraic object, a sheaf. And now for people who know about sheaves, I can just say you take this sheaf and you take its decomposition into indecomposables, which is unique up to by the Kroll-Schmidt theorem for the category of constructible sheaves on the line, and then this gives you an association of births and deaths. Okay, so if you don't know what that means, I mean, traditionally in lectures on this, you spend a whole hour talking about how you associate the individual deaths with the births. So let me just tell you, then you can accept as a fact that there is a canonical way to do this, which is not obvious. It's not even obvious geometrically. You have to pass to some algebraic object in order to even see that you can do this. So anyhow, out of any complicated space in Euclidean space, and for any integer, in this case 1, we get a scatter plot like that, and we think of this as a statistical thing, and we're going to use that scatter plot to tell us information about the object that we're studying. Let me just, for people who may not like homology, let me just tell this in a different way. This picture has an Alexander dual. Alexander was here at the same time as Lefschetz doing this, and as Morse doing it at the same time. So here's an Alexander dual description. Suppose I have, I'm going to just say use a similar thing like that. Suppose I have my object and it happens to be a C because that's a semicircle because that's what I can draw. And I, instead of changing the object, I'm going to take a disk of radius r. So here's a disk of radius r. This disk can travel inside here, but it's trapped. It can't get out. It sort of forms a cage. In the, I guess in the language of a lecture we had last time, it's pinned in the sense of robotics. It can't get out. If it were a smaller disk, it would be able to get out. If it were a larger disk, I wouldn't be able to fit it in inside. So there is some range of sizes of disk which is pinned, but still I can fit them in the interstices of the material. And so this is the birth point is the size of disk where it can escape. The death point is the size of disk where I can no longer fit it inside the material. Okay, well, this is something that that actually material scientists look at. What sorts of things you can fit. I mean, if you actually had a branched polymer, you'd actually care that the thing makes little cages that will hold particles of a certain size. In 3 dimensions, it's the same deal. If I had a sphere, I mean, there'll be a certain size sphere that won't be trapped inside at all. There'll be another size sphere which is too big to put inside there, and so then I look at the sizes of spheres which are in between. So what I'm actually doing is for, I mean, this group for a given level here is telling how many different connected components of pinning there are. By the way, this brings me to the first point of computer science. You could imagine calculating that using exactly the description I've just given you. The pinning space, that is, for a given size, the set of all spheres which can fit inside this thing is the type of space that computer scientists are fond of pointing out. You can compute everything about them, including their homology. If we had to do it that way, we would never be able to do a plot of the sizes we're getting or get answers of the accuracy we're getting. So one of the magic things of a century's worth of topology is it has given us algorithms, and there are algorithms for calculating this efficiently. I'm not going to go into that. One other comment, Alexander's picture of H1. I mean, this is H1 of the 3-dimensional object. So I'll just draw Alexander's picture, but I won't say much about it. His picture would go like this. So I'm in 3 space now. I take a plane in 3 space and have, say, a circle in that plane. And then this won't pin a this won't pin a sphere, but it will pin a sort of a thickened snake. So by the Alexander duality picture of in this case has to do with sort of thickened tubes that you can pass in between it. It's complicated to say without using the language of homology exactly what aspect of them I care about, but in any case, materials scientists care about this as well, because if you actually have a branched polymer, it's sitting in a melt, and then you have all these other polymers snaking in around it, and nobody has a good way of understanding that snaking process. Okay, so that's the method.
What about cavities? So in 3D, you could have a place you couldn't get to.
Absolutely. I should show this slide. This is H2, but of a Brownian tree in 3D. So this Brownian tree is just a one-dimensional thing. Nevertheless, it is enclosing cavities. And so this is kind of a mathematician's thought diagram, but you could trap something inside with a whole bunch of one-dimensional things snaking around it. You notice there is actually already we see a significant difference that because it's a one-dimensional thing, it captures sort of very small snakes, but it captures only very large cavity. I mean, it's not very good at capturing cavities. The H2 and the H1 picture look very different from each other, but they're both telling a story.
Are these from one given Brownian tree, or is it an average over many?
Come to my rescue.
Oh, these
this particular
each of these
picture.
diagrams are from only one.
Yeah.
But the later data is from many.
Right. Later I'll be showing you smooth curves. To do that we had to average many. This is, if we average many here, actually what happens is if there are too many dots, it's all black. You don't see anything. So.
Is it obvious why it's exponential, why it's a straight line, the edge of this?
Yes, I should say everything that happens really to the left of 10 to the 0 can sort of be explained geometrically on the level of sort of small ball interactions. And if you think about it, yes, this line consists of, well, sorry, that one I haven't thought through, but the one on the previous slide where you get a very, very thick line running up the left-hand edge, that's all caused by 3 consecutive balls all interacting. So it's junk so far as, well, unless you care about things on the ball level, it's junk so far as we can tell. Okay. Now, what cases? So I'm going to talk about these cases, and let me give, again, this is a whole subject, but let me give an introduction for. So all of these, their mathematical idealization you can think of as a whole bunch of balls which are tangent to each other. In fact, a contractible set of balls which are all tangent to each other. So here's my sort of fast introductory way of telling you what the difference is among these 3 things. Suppose I already had, whoops, they're all supposed to be the same size. Suppose I already had a sequence of 3 balls like this, then what could I do? So for the branched polymer, the idea is that what you do is you fit this ball in every place you can where it's tangent to all the others and weight them all equally. By weight them all equally, I mean they'll have one point of contact and use the distance measure in the point of contact. So all of these get weighted equally. In particular, I could attach it here, in which case it would no longer be a line, it would be a tree. Okay, so that's the branched polymer. For the Brownian tree, I start this ball at infinity and start it doing Brownian motion, and it does Brownian motion until it hits this for the first time and then it sticks. So again, it can conceivably go to every possible point on here, but it won't be the same measure exactly for the Benjamin Franklin lightning rod effect. It's much more likely, if Brownian motion is much more likely to hit on the ends than it is to hit here. It sort of has to really aim straight. So it'd be more extreme if it were longer. So again, It's a different measure on the same space, but now the measure is lower here and larger on those ends. Frankly, finally, for the two-dimensional self-avoiding random walk, I insist that the topology should never change. So I won't allow to put it on this tree because now I'd have a tree touching three things, and that would be the sort of a Y in the tree. So I want it to be sort of homeomorphic to a line. So I only allow it to be tangent to the two ends. But again, I take equal weighting of all positions which are tangent to the two ends, and I insist that it not overlap with. In all cases, I want it not to overlap with anything I've already done. Okay. So let me. The branch polymer, I've already said. I mean, people do actually use this as a model for a branch polymer in a melt. Like everything, the mathematical model is simpler than the real world. I mean, the actual shape in a melt will depend on characteristics of the melt. Let's see. Okay, here's a picture of a self-avoiding random walk. So it's long and it's very, well, I can't even fit the whole thing on. It's a sort of a very squiggly thing. And again, you can see that there are these, I mean, it's hard from where you're sitting to see that this isn't an actual loop, but as soon as I expand epsilon a little bit, it will be a loop. So all of these things can happen in 3 dimensions as well as 2 dimensions. So there's a picture of a Brownian tree in 3 dimensions. The Brownian tree, as I understand it, actually comes up. I haven't seen this, but so what they did is they had a solution of copper sulfate, and they passed current through it, and then the copper started precipitating along the because of the current, and you got this, which is a reasonable approximation of a Brownian tree. So that's an actual photograph of a real physical sample. Okay. So those are the models. Now let me talk about what we found. So what's the difference between these two? Actually, there are several differences, and some, well, one of them we were able to measure, another one we weren't. Oh, wait, sorry, I forgot. I forgot an extremely important point. For all 3 of these, if you were to try to simulate them in the way I've said, it would be hopeless. Even given the largest computer that the Institute hopes to acquire, I mean, you couldn't get a sizable thing. I mean, just think about it. Here, in either the Brownian tree or the branch polymer, you're sort of adding this thing. I mean, it's very simple to see this neat picture, but once this has several thousand balls in it, you're trying to see where you can add a ball, and you don't even know where you can fit that ball. So this space of possible tangent, I mean, here there's a clear space of here there's a space of possible points of tangency, which goes from here to here, from here around to here, like this. So for each one of those points, there's a unique guy which is tangent, and sort of being tangent to both of them is infinitely unlikely. So if you were to try to calculate that for an extremely complicated thing, you'd spend all your time. You just couldn't possibly do it. For the Brownian tree, especially, you get into binds. I mean, the thing can sort of work itself. The thing can go along like this, come down here, and then work itself into a box. These are all circles. And then there's no way to continue. I mean, because I only allow myself to continue on the two ends with the Brownian tree. So a lot of the time, you could get both ends trapped, and you'd say, well, I'm sorry, I failed, throw it away, and start over again. Well, you'd discover you'd spend most of your time doing failed computations that you were throwing away. So all of these, I won't talk about the branch polymers. I don't know the history. So sorry, the Brownian trees, because I don't know the history so well. But these two required both a theoretical and a computational advance, and I've given the credit here. This is the same Alan Sokal as the Sokal hoax, but his idea here was just brilliant geometric idea. All I can say is I would love to spend some time talking about the ideas that they had, but they were sort of completely reconceptualizing the problem, the geometry behind the problem, and as a result of that reconceptualization, it was possible to actually do simulations of the sizes that I have been showing slides of. Okay. So now I'm back to this, and I want to look at the differences between this. So what we did is, well, maybe I'll describe what we did and then come back to show you the pictures. So here's a scatter plot for the two-dimensional branched polymer. So you'll see what I'm talking about. So we cut it off here at so you have this picture, and then all this stuff. And as I already said, everything that's happening over here on the left is junk. So we cut off all of that junk just by forgetting about it, and then we counted then we broke this up into a bunch of bins of length 0.2 and counted how many points there were, or what fraction of the points lie in each one of these bins. So the point of this, we've thrown away the junk, and we've integrated out the size parameter, and we're looking only at the shape parameter. Presumably, the size parameter doesn't, well, I'll get to why the size parameter shouldn't matter so much, but okay. And now, if we divide one of these by the other, here's what we get. Right. So in most of the bins, there's approximately the same fraction, but in the bins very near the top, there's a lot more. The top two, or especially the top one, there's a lot more stuff in the branched polymer than there is in the Brownian tree. 16 times as much, or 2 times as much in the next bin. So remember what that means about our picture. That means that in the Brownian tree, we're going to see more of these things for, so here's where the difference is. That means theta is very close to pi over 2, so we're going to see lots of pictures like this, things which almost close. Lots more in them. All right. So now I'll go back to my picture with the two things drawn on the axis. And well, I don't know, at least when I stare at this, well, not at first I must say, but this jumps out at me now. I mean, look at all these things here which very nearly close. Whereas here, I mean, you'll have even very deep gulfs which end up not closing so much. I tried to explain this phenomenon to myself, and I don't have a good explanation, but here's so one of the amazing things that Ben Franklin discovered is if you have a house with two gables, if you put a lightning rod on the two ends, you've protected the whole house. And I must say, when I read about this in high school, I always wondered, how can you protect the whole house with those things? Well, I mean, that's what's going on here. Somehow, Brownian motion does not go in between these two things and fill in this gap, whereas the branch polymer thing does make them very close. Maybe it's a good time to pause and comment about something which I perhaps should have said earlier. Most of the methods of topology don't apply to these spaces. I mean, these spaces are nowhere differentiable. So smooth methods won't apply. As I already said, they're contractible. So we're looking for quantities which we can measure, which have a sort of, which I think Poincaré would recognize as topological, which can show interesting differences like this. Actually, since starting this, I must say, I go through the woods and I see, I mean, the actual trees are really different so far as this vertical parameter are concerned. Some trees send out branches like this that do that, and some trees don't. Okay, so that's the difference in the shape parameter. So let me tell you about the difference in the size parameter. So the idea is that if a sample is self-similar, then this density should grow should grow exponentially on each horizontal line. What that means intuitively is that if I have roughly one gulf on a very large scale of a certain shape, then with the same shape I'll have maybe 2 or 3 gulfs on an intermediate scale. On a finer scale yet, I'll have even more gulfs, and so on. So this gives us a test for, so I should say, I don't have a precise statement. One of the reasons I don't is that I don't have a precise definition of statistical self-similarity. So if somebody can help with that, that would be nice. But anyhow, this gives a new sort of dimension which you can measure this way. What you do is you take you take everything. Well, the simplest form of it, you take all the dots to the right of a certain point, and then that will give you a value at that point, and then you move this point here, and so that will give me by definition an increasing function because I'm only adding dots. So the function goes like this. I count the dots like that, and then I see how that total number increases as I go on. But I expect end effects. So we plot that on log paper and see if it's growing exponentially. And so let me first of all report our answers. So is there a homology dimension in these situations? And well, I mean, we have enough data now that we have these answers, mainly because of these algorithmic breakthroughs that I've been talking about. So we're pretty confident about this. Wait, I have this wrong.
No, that's
This is.
oh.
It's up here.
Oh yeah, it is.
Somewhere. Here it is. Okay, so the idea that these were not statistically self-similar, that was sort of around various other people had applied various other tests and decided they probably weren't. We think they're not. So far as we know, there was no previous conjectures about this, and we conjecture that this is statistically self-similar with dimension 2. This is not. There is one of the reasons we did this was to make sure that our stuff was working. Tom Spencer suggested that we should look at self-avoiding random walk, where there's a whole conjectural theory because it's related to SLE and to the boundary of percolation at the critical threshold. And so there they conjecture the dimension is 4/3. That's what we got. Of course, this comes with an error bar, but a rather small one. You'll see in just a moment. So let me show you the data for some of these. So first of all, this is the data for the first homology of the branch polymer in dimension 3. Perhaps on a scale like that, it may not look so good. If you blow this up, it's extremely linear in that region. I mean, this is not a smooth curve, which is approximated by its tangent. We can understand why it, as I mentioned, when you get over here, you get effects of individual balls interacting with each other. And so we can, anyhow, you wouldn't expect the thing to be accurate there because we're not approximating a branch polymer on these very small time scales. This is like the distance scales. This is like the distance scale of a single ball in our polymer. And so we'd have to go much smaller to approximate it there. Here, it goes below because we're reaching the edge of the sample size. Our branch polymer, the largest we can compute, is so big. If we could go on, it would have other gulfs of a larger size, and those would have influence. So what we believe is if we did the calculation longer, this curve would remain the same. This would start drifting down here. Just to compare it, here's the same plot of the Brownian tree. And as you can see, there's just nobody would conjecture that that is linear. And if you do it more accurately, you get the same result. Here's another confirmation. So this is done using H1. So this is like figuring out what sorts of snakes you can trap in the thing. This is a dimension using H2. This is figuring out what sorts of balls you can encage in the thing. And we get a different graph, but exactly the same slope. And so this is another indication that that what we're actually seeing is real. Finally, here's the picture for the self-avoiding random walk. It's actually in the because of the immense power of Sokol's algorithm, we're able to actually go further out. Sokol's algorithm is actually a little more powerful than the Kenyon and Winkler algorithm. So once again, the same explanation. Here is an actual picture of that random walk. This is, in case you want to know, this is the scale in terms of the size of balls. So the balls are so much smaller than a pixel size in this. So once again, you see that on a very large size, there's only one thing. You go to a smaller size, there are several gulfs. You go to a smaller size yet, you see gulfs all over. And the number of gulfs of a given size increases exponentially with the size. Okay, thank you.